restart. My name is Matthew. This is my talk about shapes in clouds and patterns in large sets. So, you and I go on a walk. It's a sunny day and there's only one cloud in the sky, and I ask you the question. In that one cloud in the sky, does there exist a sheep-like shape? There's only one cloud in the sky, so your answer is probably no. The next day, we go on another walk. Now, it's not overcast, but it definitely is more cloudy. And I ask you again, now that there's more clouds, does there exist a sheep-like shape somewhere in that collection? And on the third day, being that we're in beautiful Vancouver, British Columbia, and it's pouring rain and overcast, I ask you once again, somewhere up there in the sky, does there exist a sheep-like shape? Now, in general, our question is, must every collection of clouds contain a sheep-like shape? This is equivalent to saying, a sufficiently large collection of shapes or collection of clouds, must that actually contain a sheep-like shape? Must an overcast sky in somewhere in there contain a sheep? Now, a sheep-like shape is hard to define. It's subjective, and if it were to be objective, it would be geometrically difficult. So we restrict ourselves to easier things than clouds and sheep. We change our question. Must every large set contain an arithmetic progression? Now, an arithmetic progression is a very simple geometric pattern. Essentially, in subsets of the real line, it's evenly spaced points. A KAP, a K-arithmetic progression, is written in the form x plus delta, x plus 2 delta, all the way to x plus k minus 1 delta, where x is some real number and delta is some non-real quantity. So, well, what does it mean for a set to be large? We want large sets that contain arithmetic progressions, but what does that mean? So, now I call upon you guys, what does it mean for a set to be large? Yes?
Big, lots of elements.
Yes, okay, cardinality?
Sure.
Abstract ideas, like just start throwing them out.
Density.
Density, yeah, there you go.
Positive measure.
Positive measure. Those are all really good answers. Really, it depends on who you ask. To the set theorist, he gives you something like cardinality, a finite set, a countably infinite set, or an uncountable set. To someone who studies linear algebra, he tells you something about vector space dimension, or Rn, or R2. To an analyst, he gives you something like Lebesgue measure, or the Haar measure. And to someone who studies number theory, he says natural density, or reciprocal divergence of a sequence. And to someone who studies fractals, like me, I would give you something like the Hausdorff, Minkowski, or the Fourier dimension of a set. So, in the study of patterns in large sets, we have results. The first result is an existence result. In 1920, Steinhaus proved that for every subset of the reals E with positive length, it contains a KAP for every K. Intervals, this is intuitive. We cut a interval into K minus 1 parts, and we place a point at each of the borders. That is K evenly spaced points. Steinhaus extended this to any set of positive Lebesgue measure. It has a KAP for every K. Fermat, hundreds of years earlier though, proved a different set, large in a different way. N squared is countably infinite, but it does not contain any 5 APs, or it does not contain any 4 APs. It contains infinitely many 3 APs like 1, 25, and 49, but nowhere, if you write out all the squares, will you find 4 evenly spaced numbers. I was a little disappointed this morning there was a talk proving this, but the talk didn't end up being given, and I would love to reference that, but too bad. Now, that is a avoidance result. We have a large set that somehow avoids geometric patterns. And our third idea is the Édard-Charrin conjecture. Given a sequence, an infinite sequence A, if the sum of reciprocals of A diverges, then A contains arbitrary long arithmetic progressions. This has yet to be proved. It's been around since the 1900s and some time. Results have come like Tau proved that the primes contain arbitrary long arithmetic progressions, and we know that the reciprocals of the primes diverge. So therefore the primes satisfy Édard-Charrin. Today we'll be focusing on a result from Coletti in 1998. He proved with a set that he constructed that there exists a set with full Hausdorff dimension that contains no 3 arithmetic progression. To reference, Hausdorff dimension in the subset of the reals, having it full means its Hausdorff dimension is 1. This is the inequality we'll be using today to restructure that result. The Hausdorff dimension is an extremely intricate and difficult to describe thing. To fully appreciate it, you need really heavy measure theory and apparatuses that, quite frankly, are way beyond the scope of this talk. So, due to this inequality that says the Hausdorff dimension is less than or equal to the Minkowski dimension that is less than or equal to 1 in the set of the reals. Coletti also proved this. We have that the Hausdorff dimension equals 1, and therefore Coletti also showed that his set has full Minkowski dimension and contains no 3AP. Minkowski dimension is easy to talk about, and we'll be focusing on that. Coletti's set is Cantor type. To understand Cantor type sets, we're going to be starting with looking at an easier to construct Cantor type set, the middle third set, as to warm us up for Coletti's set. So, the nomenclature. When constructing a Cantor type set, we start with an interval, we take something away from the interval, and we do this and this, all the way to infinity, and we take the intersection of all of these things. We call this, A1 is a level, and something like this is a basic subinterval of, in this case, the A2 level. That's what a level is and a basic subinterval. So, to construct the Cantor middle third set, we begin with the closed interval C0, which is from 0 to 1. Then, as the name might suggest, we remove the middle third to construct C1. And once again, as the name might suggest, and the keen audience member might hypothesize, we once again remove the middle third. We do this forever, and we take the intersection, and we get the infinite intersection of Ci is equal to C. Well, what can we say about patterns in the Cantor middle third set? The unit interval obviously contains infinitely many 4APs, but they're not very apparent. When you look at C1, however, we start to see that they exist. Marked by red dots, we have 4AP from 0 to 1/3, 2/3 to 1. When constructing C2, we now have 3 4APs. One is completely contained with the first third, one is contained within the last third, and then we have the 4AP that we constructed in C1. What can we say about the size of the Cantor set? Once again, it depends on who you ask. The set theorist will tell you it's uncountable. The analyst will say it has length 0, it's very small. But someone who studies fractal geometry will say no, it's not big and it's not small, it's somewhere in the middle. The Minkowski dimension is bound by 0 and 1 for subsets of the real line, and it turns out the Minkowski dimension of the Cantor middle third set is about 0.6. So it's medium sized. To define the Minkowski dimension, what we do is we take our set, we cover it in boxes of length epsilon, and then we count how many boxes it takes to cover our set. We shrink epsilon a little bit, and we recount how many boxes it takes. And then we let epsilon go all the way to 0, and we end up with a limit. If that limit exists, this is our Minkowski dimension. When doing the unit interval, for example, we can let epsilon equal 1/6. We need 6 boxes to cover the unit interval, and therefore we get the Minkowski dimension is equal to 1. For the unit square, if we let epsilon equal 1/4, we need 16 boxes to cover, and therefore we have the Minkowski dimension is 2. The diagram for the unit cube, beyond the scope of this talk, but it ends up being a Minkowski dimension of 3. So what can we say about the Minkowski dimension of the middle third set? When looking at the first level, the second level, and the third level, it's important to note that each level contains 2 to the n basic subintervals of length 3 to the negative n. So we let epsilon equal 3 to the negative n. If we do that, we know we'll take 2 to the n boxes to cover our set. Therefore, we get the following limit. The n's cancel, thankfully, and we get log over 2, or log 2 over log 3 is the Minkowski dimension of the Cantor middle third set. Now to construct Coletti's set, that we've got a basis for what a Cantor type set is. Once again, we start with the interval A1 from 0 to 1. Delta m, where m is the mth level of the middle thirds Cantor set, the length of each basic subinterval is 1/6 to the m-1 times m factorial. We also create a sequence we denote as j. How j works, if j was placed on the middle thirds Cantor set, we have our first C0, C1, and C2. We denote this J1, this is J2, J3, 4, 5, 6, 7. Essentially what J does is it counts the basic subintervals from the first level, from left to right, then the second level from left to right, all the way down to the very bottom. As you can see, the sequence J moves across in a pattern like that. Just as we did in the Cantor middle third set, what we need to do is break up our first level into pieces and choose what pieces we're going to keep. Delta 2 is equal to 1/12, and therefore, to cover the entire unit interval, what we're going to need to do is break it up into 12 pieces. 12 times 1/12 is 2, and that's the length we're going for. We label them starting at 0, ending at 11, and we choose the pieces whose label I is congruent to 3 mod 6. In this case, that ends up being the 3rd and the 9th piece. And this was our first level, A1, denoted J1, and A2 contains J2 and J3 as described in the previous slide. J2 ends up being 3 over 12 to 4 over 12, J3 9 over 12 to 10 over 12. Now, as we did in the Cantor middle third set and in the previous slide, what we need to do is take each of the basic subintervals of A2 and break them up into more pieces to carry them down into A3. We'll do the same thing we did before, this time into 18 pieces. So we take J2, we break it into 18 pieces, we label them starting from 0 to 17, and then what we do is we choose the ones that are whose label is congruent to 3 mod 6. This is the 3rd, the 9th, and the 12th. Yes, the 3rd, yes, okay, these ones are the ones we keep. The ones whose label is congruent to 3 mod 6, which ends up being the 3rd, the 9th, and the 15th. We introduce a new rule, however, when breaking up J3. We once again break it up into 18 pieces and label them 0 through 17. However, instead of keeping the ones whose label is congruent to 3 mod 6, we now choose the ones whose label is congruent to 0 mod 6. That being the 0th, the 6th, and the 12th label. In general, when constructing Coletti's set, to construct AM plus 1 from AM, we divide the unit interval 0 to 1 into 1 over delta m parts. We choose 1 over delta m because that times delta m is equal to 1, and that's the length we want. This divides each of the m factorial basic subintervals of AM into 6 times m plus 1 parts. First we started with 12, and then 18. So 6 times 2, and then 6 times 3. Once we split them up, we label these new divisions 0 through 6 times m plus 1 minus 1. In the first one, 0 to 11, and in the second, 0 through 18. Now, if an interval is contained within Jm and its label I is congruent to 3 mod 6, we keep it. What that means, in this example, it's easier to draw out the middle thirds Cantor set. When creating C2, if we are under J2, we use the 3 mod 6 rule. But when splitting up J3, since we're constructing C2, we don't use the 3 mod 6 rule, we now use the 0 mod 6 rule. When constructing C4, we're going to jump to J3, so everything over here we use the 0 mod 6 rule, and over here we use the 3 mod 6 rule. That's how the sequence works, and that's what gives Coletti's set a sort of memory. It can remember what happened before in the levels above it, and he uses that power that it has to show that it has no arithmetic progressions. But what we are also looking at is the size of his set. We know that each level, AM, contains m factorial basic subintervals of length delta m, with that quantity being 1 over 6 times m to the minus 1 times m factorial. So, if we let epsilon equal delta m, we know we're going to have the number of boxes with length epsilon is going to be equal to m factorial. So we arrive at the following limit. The number of boxes on top and the length of each box on the bottom. Those cancel, and because 6 to the m minus 1 grows so much slower than m factorial, as m gets really big, it doesn't really matter. What's interesting is, a side note that Coletti has in his paper is that we can replace 6 with some slowly increasing sequence. What that means is that as long as our sequence is growing slower than m factorial, this limit will still work and we will have full Minkowski dimension and full Hausdorff dimension. To show it has no 3 APs, we first need to define what is needed for a 3AP. For a 3AP, we need x3 strictly greater than x2 strictly greater than x1. And we need the difference between x3 and x2 to be equal to the difference between x2 and x1. So what we do is we fix x1, x2, and x3 in that format. Now we find k, which is a level of the set, such that delta k is smaller than the difference between x2 and x1. And k such that x1 is an element of k. For example, let's say k is equal to 2. Let's say x1 is equal to here. We'd want k equal to 2, because then x1 falls under. And then, when we construct the intervals that contain x1, we use the first rule, the mod 3 rule. This means x1 can be written in the form 6 times n1 plus 3 times delta k plus epsilon 1. The plus 3 comes from the mod 3 rule, and the n1 just tells us how many intervals into that level we are. If n is equal to 0, then we're just at the beginning. If n is really big, then we're moving along. But because delta k is smaller than the difference between x2 and x1, what that means is that x2 is spit out into a new interval. It's outside of k. It's outside of jk. And because it's outside of jk, we then use the 0 mod 6 rule to define the intervals in which it's x2 and x3 are contained. And so therefore, x2 and x3 can be written in the form 6 times ni times delta k plus epsilon I. Epsilon I is just how far into their subinterval they are. So that means x2 minus x1 is written in this form. They're the parts that are multiplied by delta k plus their epsilons. And the bottom one is supposed to be x3 and x2, that's a typo, but it is the n parts times delta k plus the epsilons. Now, we can rearrange this to show that x2 minus x1 over delta m is sum 6n2 minus 6n1 plus 3 plus epsilon 2 minus epsilon 1 over delta m, where delta m and k are the same. And x3 looks similar to the following form. Because of the nature of epsilon, though, it's an extremely small quantity. We have delta m, very small as well, and what happens is this blue part, we call it junk, because it's such a small difference that when you define the intervals, it really isn't doing too much movement. So what we can do is we can ignore it, and we can rewrite the differences into this form. x2 minus x1, if it's equal to x3 minus x2, then it should be equal when divided by delta m. But if we look at the top, this is clearly something that is congruent to 3 mod 6. And if we look at the bottom, this is clearly something that is congruent to 0 mod 6. And by the fundamental theorem of modular arithmetic, those two quantities cannot be equal. And therefore, Coletti's set contains no arithmetic progressions. That's my presentation. Thank you, guys.